So, welcome everybody to the very first episode of Tezos X-plained. And I'm very honored and very happy to have Arthur Breitman here, the co-founder of Tezos. And we're going to talk about composability today. So, Arthur, welcome. It's such a pleasure to talk to you.
Likewise.
I always remember the very first time we had a conversation.
2 years ago now.
Yes, it's 2 years now, but definitely I remember one very important thing that, but we're going to go back to it. We're going to go back to like when we finish talking about composability, I'll remind you what was the main outcome. So yes, composability, Tezos X vision. Maybe let's start with a little bit of definition. What's composability and how you see this as a fundament of Tezos X vision?
I don't come prepared with like a nice, like tight definition of composability. But, oftentimes I think like concise definitions are overrated and giving a lot of example is underrated. So I would say composability is when you can have different modules, different pieces, and you can plug them into each other, and then the whole is more than the sum of its parts. So the typical example people like to give is, Lego. Or people even say building blocks, but that's what it is. You can have very different pieces of Lego, but the thing that's great about the Legos is that they all fit in together. There's one system, and like any piece of Lego, you can fit with another piece of Lego, and then you can build all of these things. And I remember when DeFi really got its starts in 2020, one of the expressions that people had for it was money Legos. And it worked a little bit like this. You had a decentralized exchange, for example, and a decentralized exchange could be used for getting a price feed that would be used for a lending protocol, and the lending protocol would use the decentralized exchange for liquidation. You could do this, you could do these splash loans to instantly, ruthlessly borrow money, make a trade, get the outcome of that trade, and then pay back the money. So you had all of these different pieces which were built by different developers, potentially different projects, and they would interact with each other. And I think that's one of the biggest strengths of these blockchain systems that we have today and these blockchain networks is the fact that by building there, you are benefiting from this network effect of other applications which are also there and which can interact seamlessly with this one application. And so that, I think, is composability.
Okay, brilliant. So tell me what's very unique about Tezos' approach to composability.
So initially, if you look at a lot of the design for blockchains, they were all pretty much composable by default. So any blockchain has been some smart contracts. Not only was they composable, they had a very strong form of composability, which people have also called atomic transactions. So it's not just that your contracts work with each other, it's that you have this very powerful primitive of saying, I want this sequence of computation to happen, and it should either completely happen or not happen at all. In a database, you might call this a transaction, for example, where you don't want to be in an inconsistent state. So you had this strong atomicity and this very, very strong composability where everything would kind of work together. And that's extremely powerful. And, until recently, that was a default. Mm-hmm. But then we saw different ways in which blockchain needed to scale. So it's all, fun and games until the demand for transactions become very, very large, and then some blockchains cannot keep up with that demand. So people are debating in different areas, and part of the idea was, well, let's use multiple blockchains. We'll have a whole ecosystem of blockchains, and if one gets too expensive, we'll get on the other one. That doesn't quite scale because any capital that you would be using for securing the chain is going to be diluted anyway. So you don't really scale your security budget. And on top of that, you break composability because now you have to go to different blockchains. People tried to use layer 2 solutions, and I think they're quite interesting, but we'll go back to that. Mm-hmm. But if you look now at the ecosystem on Ethereum, it's extremely fragmented, with people having to go from L2 to L2 using centralized bridges. And you can't simultaneously call two contracts on the different L2s or have them interact seamlessly, let alone with atomicity. People saw sharding solutions, but also oftentimes the sharding solution would break a lot of composability. And a few years ago, I think that Solana marketed itself heavily as favoring composability. And the way they said is like, look, we're just going to monotonically scale or layer 1. We're not going to try to do any of those like scaling approaches. What we're going to do is we're just going to throw more compute, more performance, more optimization just at the layer 1 monolithic level, and that will be enough. And then you'll preserve all these benefits of composability. So the path I'm interested in for Tezos, which is the Tezos X path, is yes to layer 2s, yes to having multiple layer 2s. I think it's good to open many doors and have many options. However, the insight, which is a bit subtle, is that even if you want to scale monolithically, you're better off doing this with an L2. And that's very, very counterintuitive to a lot of people, because in people's mind, rollups were associated with wanting to have many rollups in parallel. So what you could call horizontal scalability. But actually, they are a great way to scale vertically. And that's not obvious at all. And there's reasons behind it. One is that we have good ways of doing, of sharding data availability, but you need a rollup to consume it. You can't consume data sharded data availability directly on L1. The economics and the game theory of a rollup is very different than that of an L1. In an L1, you rely on an honest majority assumption. And the honest majority assumption is the worst thing in all of crypto, in all of blockchains. On the one hand, you have these guarantees with cryptographic signatures, and oh my goodness, it would take more energies than the entire universe in order to break this. So you have this like astronomical guarantees. And then underpinning all this, you have like, oh, well, maybe this validator in China is not going to collude with this validator in Canada, and that's what our security depends on. And as much as possible, you want to get rid of that. You want to get rid of this dependency. In a zero, in a validity rollup, also known as ZK rollup sometimes, but validity is a better name, you have no honest majority assumption. And you have not even a single actor being honest assumption. You have a cryptographic proof of execution. And that's a way of scaling that I described in a 2017 blog post when I was arguing against sharding. In an optimistic rollup, you need a single honest node. A single honest node is a much better assumption than honest majority, right? Honest majority, who knows? But is there one honest person willing to run this thing? It's almost biblical. Like if you can find me one honest person, and I would argue that if there's not a single honest person in the world who cares enough to make this protocol run, then maybe it shouldn't run. So because of that, when it comes to the layer 1 and consensus, if you need to be as decentralized as possible, you need to make it very cheap. You need to allow as many people as possible to participate, and that means accepting longer latency. It means accepting lower hardware requirements. And to this day, you can run your Tezos L1 node on a Raspberry Pi. However, if you move things to an L2, then all of a sudden you're like, okay, well, if all I need is a single honest party, I can make more assumption about the resources of the honest party. I can ask for a lot more, computing power. So a lot of the issues you would have with scaling an L1 go away when you scale a single L2. And that's, I think, what's unique to the approach for scaling. Tezos is like, yes, it's an approach based on L2, but with a monolithic L2, with a big monolithic L2, you can keep all of the composability while at the same time having the benefit of scaling your data availability layer and all of other things, and keeping the L1 very, very cheap to validate.
Yep. So I can see there are few keywords here that are actually the challenges of getting composability into our ecosystem. So let's focus on three of them. What would be the biggest challenges in your opinion for now, just for composability and Tezos X booming, let's say?
I mean, the challenge is building it. This is not easy.
Yeah.
Unfortunately, this is complicated to get this to work.
Yep.
There's a lot of moving pieces.
Yes.
There's a lot of optimization you need to make in the performance. It's a whole complicated stack. It's not complicated. Once it works, it works. It's not complicated to the user. The whole point is to make it easy for the user and developer. But to build a backend to all this is not an easy. It's not an easy feat. So I would say that's the main challenge. I don't think we have challenges to composability today on Tezos because most activity is taken based on L1.
Yeah.
So now some of it is taken based on Etherlink. So indeed, now there's a little bit of splitting of the activity. But one of the goals is precisely to take this L1 activity on Tezos and actually move it to a rollup. Initially, potentially a rollup that runs some side by side with Etherlink, That's what there's a code name for this, which is Tezlink. I don't know if it'll stay as a name, so that they can have like high composability with each other.
Yeah.
But then eventually, rolling everything into a big rollup, which doesn't mean that you can't run smaller rollups in parallel if you want to, but you don't necessarily have to. One of the areas as well of composability is I've talked about it from a very abstract perspective. The contracts can call each other, but one of the things that's a big part of TezosX is having multiple programming languages, and that's also a form of composability, right? If you can have a contract written in EVM or Solidity or compiled to EVM interact with a contract written in Michelson, or one written in Python or JavaScript or Java or .NET. All these languages being able to talk to each other, that's also a form of composability. So I would say there's a bit of a continuum between what people might call like strict composability and interoperability.
Yeah. So I think it's a great point here, and it leads us to the conversation that we had in Paris. And my key takeaway from the conversation back then, it was to give the experience to the user with blockchain under the hood. Like they don't even realize that they're using blockchain, but in fact, blockchain is the core of the applications they use, and it's a backbone of the activity for the end users. Yeah, and you mentioned. Of course, JavaScript, because I'm a great fan of justice and I'm a great advocate for this technology. And composability, from what you're saying, yeah, it's not only focused on blockchain, it's focused on tech in general. And if we have like moving parts even outside Tezos, and we can make them work with our tech, it's brilliant. It's opening a lot of doors that were not accessible before. Yeah. So, for example, let's say we look at tech as a bigger picture, yeah? And how do you see, because of course you mentioned that Tezos will be the cloud for blockchain projects. How do you see, as a player on a bigger tech space?
I'm not sure I agree.
Yeah. Okay.
So I don't think it's going to be a cloud for blockchain project. I think the thing that I said is that, initially when you look at blockchains, when the cost is very, very high of running anything on a blockchain, you want to make sure that there's a very, very strong evidence match between what you want to do and what a blockchain does.
Yeah.
And a lot of the time that meant you need a lot of censorship resistance. Mm-hmm. For example, you really need payments. You need all of these attributes. And there's all diagrams for this, which is does your project need a blockchain? And there's different version of this diagram. And, one of them has a single line that says no. And I think that's, that's my attitude for 95% of the use cases that people bring for blockchains. I'm super excited with the use cases that do exist. But by and large, this is, for the past 10 years, people have tried to shoehorn the technology in a lot of use cases that it was not really fit for. However, I take a bit of a radical stance. Mm-hmm. The most radical stance essentially is unless you're doing something that needs, complete decentralization and, that every government worldwide is going to try to actively ban, then why would you use a blockchain? But for that argument to make sense, it has to be super expensive to use a blockchain. It's indeed, if you are going to look only at the most defensible, strongest use of the technology, you're going to be pretty limited. As the cost goes down, it's why not? Because the argument for this is well, if that's the case, why doesn't your project use AWS? And the reason is well, maybe you don't want to be dependent on a single vendor, on a particular vendor. Maybe you want better interaction with other projects. Maybe you want to have a native way of payment that's going to work more smoothly in a lot of different jurisdictions. So there's a lot of friction argument that it's not just about can you do this somewhere that doesn't use a blockchain. It's what is the friction of doing this outside of the blockchain ecosystem? I think is a better way to frame it. And as the cost goes down, the amount of friction that you need to experience outside of a blockchain environment to justify using a blockchain for lower friction becomes much lower. And so in some sense, it becomes a little bit of a cloud-like backend in a sense of well, I'm not saying you're going to run heavy computation on the chain directly, but what I'm saying is, if you're building some sort of application with some of a state logic that can process some form of payments, putting a lot of that logic on the chain makes sense. if the cost is really truly minimal.
Yeah, absolutely. Okay, I see it. I see it's different now. So I think it's a good reducing friction. Yeah. So composability is all about reducing friction in many different ways.
Yeah, absolutely.
Yeah. So
So there are ways to get composability between different systems. You can do double commits, for example. A common problem that people have used to illustrate these issues of composability is the airplane ticket and hotel problem. So in the airplane ticket and hotel problem, you want to go on a vacation, and you want to book a hotel, and you want to book airplane tickets. And of course, they have limited availability. But you do not want to book a hotel unless you're sure that you're going to get your airplane tickets, and you don't want to go to your airplane ticket until you're sure that you get the hotel. If you have a single blockchain, it's very easy. You send the transactions for both, and atomically, the transaction is either going to succeed or fail. Mm-hmm. So that's simple. What if you are now using two shards, for example, or two different blockchains or two rollups? How does this work? And so one is that, well, you're going to take the risk that it fails. That's not great. And the other option, which is how it would work, is that you would go on one, you would purchase an option, a time limited option. So, you purchase an option on a room, and maybe there's like a small cost for this. You're going to say, like, hold this room for, maybe the room costs £100. So you're going to pay £1 to hold the reservation for like an hour. And then you go to the other one, then you buy your ticket, and when you confirm the ticket, you go back to the other things. Or you could have synchronization point and you have double commits. The point is, like, it's possible to get composability. It just gets expensive and very difficult in practice. So I agree with you that it's about minimizing friction.
Yeah. Composability solves a lot of problems.
Yeah. I would say the main vision is really scaling the chain and allowing many more applications to come online. But I would say composability was more of a design requirement, sense of like you need to keep that. So we did a demo at TestDev actually 2 years when I first thought you were interviewing me, where we demonstrated 1 million transactions per second, but the demo was across 1,000 rollups in parallel. Yeah. So it shows like a lot of capacity on the chain, but they were not, they would not have been completely composable, right? You can move assets. So the argument against composability, by the way, people have been making, which is there's some value to it. It's like, look, the main composabilities that people want is being able to move assets from one place to another. Yeah. Right? They have their funds somewhere, they want to move their funds somewhere else. They don't want to use an insecure bridge. And so if you can solve that, you've solved like all of the problem. It's partly true. It's not completely true. You really benefit from having all these different applications being able to talk to each other. A good example for this is, by the way, I think it's part of the Unix philosophy in the Unix operating system. The idea was to create a lot of small utilities, which would each do this one task, but which could be easily composed to make bigger tasks. Yeah. It's also a way of alphabets,
Yeah, it reminds me to one of my previous companies where I worked for, we had big monolithic architecture, and then we switched to microservices. And yeah, that improves, for example, it improved the latency. So do you think it will be challenging to keep a good latency when it comes to communicating between each module?
Well, the point here is precisely that you have something that's monolithic. So I'm surprised that it depends on your context. I think if you're waiting on a lot of reads, for example, like the micro service architecture could help your latency. Yeah. But here, essentially, you are, everyone's reading from the same. So you already have some asynchronous primitives inside the protocol, so it's capable of doing this type of things. And when people think of latency here, mostly they think about like the latency for including transaction on a chain, as opposed to anything else. And there's basically two ways you can go about it. One is that you can try to have a shorter block time. That's the easiest, and of course the Tezos block time has been going down steadily. Yeah. But I would say they are marks, and it's almost a political decision what block time you want to have. So there's a block time you could have, which is to say, I want everyone to be able to run a node over Tor. And if you run that, maybe you want a minute block time, maybe you want even like longer block times for people to be able to participate, and that's going to be a constraint. If you say, you know what, I'm not going to have Tor, but I want people to be able to do this in the middle of a forest, or on a cell phone connection, or maybe on a Starlink connection now, not necessarily in a data center. And then I think now you can go down to a few seconds, but you don't want to be much lower than this either. There's also like more chances for things to go wrong and to start telescoping if you do that. So how do you go below a second? One option, and I've discussed this in the videos a while back, is to basically get some commitments for bakers. So in Tezos, you know in advance who's going to create the next block. So you could have these people, say like, look, I'm going to accept transactions, and I'm going to give you early guarantees that I'm going to inject, I'm going to accept your transaction in my next block. So it's transforming every single baker into a mini sequencer for a minute. I know Ethereum is now looking at this for rollups out there. Now I want to do base rollup, which are rollups without a sequencer, with confirmation. And it's funny because my initial idea was really in this direction. I have the videos where I talk about like confirmation into blocks and like basically you need a sequencer. And now I'm moving in the other direction. So now I think sequencers get a bad rap. They've been overloaded with other functions. So like, for a while, it's different now, but for a while, if you look at the sequencer in Arbitrum, it was the only one who was able to it would bridge your token immediately. It would be able to create, do all the fraud proofs, do all the posting and so on and so forth. So the sequencer was basically the actor controlling absolutely everything about everything. If you design a sequencer properly to only do its job, which is sequencing, nothing else, and you make it revocable so that anyone can be elected sequencer, then essentially that party doesn't have that much power anymore. And if on top of that you had a small layer of encryption so that the sequencer can't even really see the transaction, then it doesn't really matter who the sequencer is. Like the worst thing they could do is randomly shuffle transactions, or they could like make you believe that your transaction was accepted and then they switch, but then it becomes visible to everyone else. So they can't steal funds, they can't do anything. So again, in the same spirit of, I think we should be fine with like protocols that have a single party majority assumption. I think we should also be fine with like, look, there's a party that's a sequencer and they basically have no power. I think it's always important to like keep options open and look at many different ways of doing this. I'm not saying the sequencers in any way. I like, like having a baker be a sequencer for their own block is also an interesting idea. I just think it's like more of a lift technically for a small advantage.
So this is like, let's say, a new chapter for not only layer 1, layer 2, but in general, I think the vision is evolving still, like in many different ways. But
the chain is evolving. I mean, it's responding to it's also responding to new information, right?
Yeah.
You see what's happening, you see what the use cases are, you see what people want, you see what makes sense, what doesn't. It's it's a very different environment today than it was 10 years ago.
Yeah. It's very significant change in many different ways, and like even more people involved, more users, more traffic, more transactions, more everything. And composability is enabling scaling, and this is like the most important part of it.
I know, but going back 10 years, I remember the problem that people thought were going to be important and turned out to be not important at all.
Yeah.
Interesting. Like the main one was like long-range organization for proof of stake. That's what everyone focused on. I focused on it. It was like huge part of the design of Tezos. And it turns out like my intuition at the time was like, it matters less than people assume, but it's very important to like give the strongest possible answer to this. And then it's like, it mattered even less than that. And I think it makes sense, but that's also like a reaction of how the space has evolved. Because the space had been pushed like completely into the underground. Then I think I think the trade-offs will be different.
Thank you so much. I think that's it. That's all I wanted to know. Thank you so much, Arthur.
All right, thank you.
It was a real pleasure.
Likewise.